Hi everyone, I am Puan Ani Zulhana from PTE Tinggi Setapak, Kuala Lumpur. Today, we are going to continue Chapter 13 on capacitors. We are going to learn about 13.4 capacitors in series and in parallel, and 13.5 energy stored in a charged capacitor. Our learning outcome for today is to be able to derive and use the formulae for effective capacitance for capacitors in series and in parallel. Capacitors in parallel. Two capacitors connected as shown in the diagram are known as a capacitors in parallel. Both the capacitors are charged to the same potential difference. The total charge Q stored by both capacitors is the sum of the charge on the individual capacitors Q1 and Q2. This is because the voltage across the capacitors are the same. Hence, the charges stored in the capacitors are Q1 equals C1 times delta V, Q2 equals C2 times delta V respectively. If we were to replace these two capacitors by one equivalent capacitor with the capacitance of Ceq, then it will be C equivalence equals C1 plus C2. Thus, the charge carried by the combined capacitor Q can be calculated by the formula of Q equals C equivalence times delta V. Since the charge stored on the capacitor Q is equals to the capacitance of the capacitor C times the potential difference across the capacitor plates V, and the total charge stored on the capacitor plates Q is equals to Q equals Q1 plus Q2. Therefore, by substituting Q equals CV into Q equals Q1 plus Q2, then we can get C equivalent times delta V equals C1 times delta V plus C2 times delta V. Hence, delta V times C equivalence equals delta V times C1 plus C2. Then, dividing by delta V, C equivalence equals C1 plus C2. Thus, the equivalent capacitance of a parallel combination of the capacitors is the algebraic sum of the individual capacitance. Now, we will move on to the capacitors arranged in series. Two capacitors are connected in series as shown in the diagram. The left plate of capacitor 1 and the right plate of capacitor 2 are connected to the terminals of a battery. The other two plates are connected to each other. When the battery is connected, electrons are drawn out from the left plate of C1 to the positive terminal of the battery and continues to flow to the right plate of C2. As these negative charges accumulates on the right plate of C2, an equivalent amount of negative charges is forced out of the left plate of C2, and the left plate therefore has excess positive charges. The negative charges from the left plate of C2 accumulates on the right plate of C1. As a result, all the right plates will end up with charge negative Q, and all the left plates will end up with charge positive Q. The charges on capacitors connected in series are the same. Q equals Q1 equals Q2. The potential difference delta V across the battery terminals is shared between the two capacitors. The equivalent capacitor has the same effect on the circuit. An equivalent amount of negative charges is forced out of the left plate of C2, and the left plate therefore has excess positive charges. The negative charges from the left plate of C2 accumulates on the right plate of C1. As a result, all the right plates will end up with charge negative Q, and all the left plates will end up with charge positive Q. The charges on capacitors connected in series are the same. Q equals Q1 equals Q2. The potential difference delta V across the battery terminals is shared between the two capacitors. The equivalent capacitor has the same effect on the circuit. As the series combination, when it is connected to the battery, therefore, the potential difference across the equivalent capacitor delta V is equal to the charge stored on the equivalent capacitor divided by the equivalent capacitance. Hence, the voltage for capacitor 1 and capacitor 2 are delta V1 equals Q over C1. Delta V2 equals Q over C2. Since delta V equals delta V1 and delta V2, therefore, Q over C equivalence equals Q over C1 plus Q over C2. Hence, 1 over C equivalence equals 1 over C1 plus 1 over C2. As a result, the inverse of the equivalent capacitance is the algebraic sum of the inverses of the individual capacitance. So, what will happen when capacitors in series are connected to a voltage supply? No matter what is the value of its capacitance, each capacitor in the combination will store the same amount of charges. This is because any of the plate can only lose or gain the charges, gained or lost by the other plate that it is connected to. The total charge stored by a combined capacitor is a series circuit is equal to the charge stored on each individual capacitor. This is because the applied potential difference is shared by all the capacitors. Let's move on to example 1. Find the equivalent capacitance between A and B for the combination of capacitors shown in the figure. All capacitance are in the units microfarads. The solution for example 1 is: first, the 1.0 and 3.0 capacitors are in parallel. Same goes for the 6.0 and 2.0 capacitors. Hence, we use 1 over C formula. The answer we get is 4.0 and 8.0 microfarad respectively. Next, 4.0 and 4.0 capacitors are in series. We use series formula to get the answer 2.0 microfarad. Same goes to 8.0 and 8.0 capacitors. Finally, 2.0 and 4.0 capacitors are in parallel again. And our final answer is 6.0 microfarad. Now, we will move on to example 2. Determine the equivalent capacitance as shown in the figure. All the capacitors are identical and each has capacitance of 1 microfarad. Let's check the solution for example 2. First, we label all the capacitors in the circuit as C1, C2, C3, C4, C5, and C6. To find the equivalent capacitance, it is easier to solve it from the left end of the circuit to the right end of the circuit. Since capacitors C1, C2, and C3 are connected in series, we will use 1 over Cx equals 1 over C1 plus 1 over C2 and plus 1 over C3. Hence, Cx equals 1 over 3 microfarad. Since capacitors Cx, C4, and C5 are connected in series, then 1 over Cy equals 1 over C2 plus 1 over C4 plus 1 over C5. Since capacitors Cx, C4, and C5 are connected in series, then 1 over Cy equals 1 over Cx plus 1 over C4 plus 1 over C5. Hence, Cy equals 1 over 5 microfarad. Capacitors Cy and C6 are connected in parallel, hence the equivalent capacitance is given by Cy plus C6. C equivalence equals 1 over 5 plus 1 microfarad. C equivalence equals 6 over 5 microfarad. Now, we will go to the section 13.5, energy stored in a charged capacitor. Our learning outcome is A. Use the formula U equals half QV. U equals half Q square over C, and U equals half CV square. Energy is supplied from a power supply or any other source to charge a capacitor. A charged capacitor can supply the energy needed to maintain the memory in a calculator, or the current in a circuit when the supply voltage is too low. When the power supply is turned on, the capacitor gets charged. the plates of the capacitor acquires positive and negative charges. Hence, an electric field exists between the plates of the capacitor. This allows electric potential energy to be stored between the plates of the capacitor. How much energy is stored in a charged capacitor? When a capacitor of capacitance C is charged by a potential difference delta V, charges flow from the voltage supply into the capacitor until the potential difference across the capacitor Vc equals the terminal voltage delta V. The work done in charging the capacitor is equal to the electric potential energy U stored in the capacitor. The potential energy stored in a charged capacitor can be stated in any of the following formulae. U equal half QV, U equals half Q square over C, and U equals half CV square. This result applies to any capacitor regardless of the geometry. We see that for a given capacitance, the stored energy increases as the charge increases and as the potential difference increases. The amount of energy stored in a capacitor depends on the amount of charge stored on the capacitor plates. The voltage between the plates and the capacitance of the capacitor. Energy is stored in a capacitor due to the electric field created between the plates when the capacitor is charged. The graph shows how the potential difference across the plates of a capacitor depends on the charge stored. When a charge delta Q is added to a capacitor at a potential difference V, the work done is delta Q times V. The total work done in charging a capacitor is the sum of charges times the potential difference across the capacitor. Hence, the shaded area below the graph represents the energy stored in the capacitor. Therefore, the energy stored in a capacitor can be calculated from a graph of charge against potential difference by calculating the area below the graph One device in which capacitors play an important role is the defibrillator. Up to 360 joule is stored in the electric field of a large capacitor. In a defibrillator, when it is fully charged, the stored energy is released through the heart bipedals that are placed on both sides of the victim's chest. The defibrillator's pedals are applied to the patient's chest, and an electric shock is sent through the chest cavity. The aim of this technique is to restore the heart's normal rhythm pattern. Let's look at example 3a. A 3.00 microfarad capacitor is connected to a 12.0 volt battery. How much energy is stored in the capacitor? Let's try to solve the problem. We are given capacitance of a capacitor C and voltage supply V, and we are asked to find the energy stored in a capacitor U. We use the equation energy is stored in the capacitor U equals half CV square. Entering the given values equals half times 3.00 times 10 power of 6 times 12.0 square equals 2.16 times 10 power of 8 joule. Next, look at example 3b. If the capacitor is connected to a 6.00 volt battery, how much energy is stored in the capacitor? Let's try to solve it. B. Use U equals half CV square. Entering the given values equals half times 3.00 times 10 power of 6 times 6.00 square equals 5.40 times 10 power of 7 joule. Now, we will move to example 4. Capacitance of a heart defibrillator. A heart defibrillator delivers 4.00 times 10 power of 2 joule of energy by discharging a capacitor initially at 1.00 times 10 power of 4 volt. What is its capacitance? Let us try to answer the question. Let us look at the solution, we are given energy stored in a capacitor U and voltage supply V, and we are asked to find the capacitance C. We use equations. U equals half CV squared. Hence, C equals 2U over V squared. Answering the given values equals 2 times 4.00 times 10 power of 2 divide 1.00 times 10 power of 4 square. The answer is 8.00 microfarad. So, after today's lesson, I am sure that all of you will be able to solve questions regarding capacitors placed in series and in parallel, and energy stored in a charged capacitor. That's all from me. Thank you and see you again.
Hi, I'm Puan Fatima, your Form 6 teacher for our physics lesson today. Today's topic is alternating current through a resistor. Let us talk about the difference between AC and DC. The letters DC stand for direct current, and it generally means the electron flows in a single direction. AC stands for alternating current, and it means the flow of electrons changes. For example, when a battery is connected to a DC motor, it begins to flow in a single direction. What will happen if we turn this battery around that reverse the polarity? This means the current will flow in the opposite direction unlike before and cause the motor to spin in the opposite direction. So let us move on to the alternating current. In this case, we are going to use a light bulb and plug it into the AC generator. We shall start the AC generator in the slow-moving coil. Notice that the pointer of the emitter deflects repeatedly from one side to the other and the bulb flickers. This shows that the directions of the magnitude of the current changes repeatedly. When the coil moves faster than before, we can see the peak current is increased. If the frequency is more than 10 Hz, our eyes cannot detect the flickering of the bulb. The pointer cannot respond fast enough to the changing current and therefore seems to be stationary. So, that is why in our homes the bulb does not flicker. The AC supply in our homes is 50 Hz. Now let us look at the AC source when it is supplied to a resistor. When it is connected to the center zero emitter, the maximum or the peak current is deflected at 3 amperes. When the AC emitter replaces the center zero emitter, the pointer shows a steady current of about 2 amperes. The current measured by the AC emitter is called the effective current or the root mean square current, the IRMS. This current is always less than the peak current. The voltage across the resistor varies sinusoidally with time. A sinusoidal potential difference can be represented by V equal to V naught sine omega t. This will form an AC wave, where V naught is the peak voltage. and the omega is equal to 2 pi f. When we connect a voltmeter across a resistor and an emitter in the circuit with an AC supply, the deflections of both meters are the same. This shows that when an AC is supplied to a resistor, the voltage and current are in phase. V equal to V naught sine omega t. From Ohm's law, V equal to IR, we can derive an expression for the current I. I equal to V over R sine omega t, where I naught equal to V naught over R. So, the expression for the alternating current through a resistor is I equal to I naught sine omega t. Let us look at the voltage time graph and current time graph. Notice that voltage V and current I are in phase. The graph shows the variations of the potential difference V across the resistor and the current I in the circuit with time t. Let us familiarize ourselves with some terms used for an AC wave. The period t of an AC is the time taken for one complete cycle. The frequency f of an AC wave is the number of complete cycles in 1 second. The unit is hertz. Since the current and voltage vary with time, the power dissipated in the resistor also vary with time. The derivation of instantaneous power for AC output is given by P equal to IV. P equal to I naught sine omega t times V naught sine omega t. So, P equal to I naught V naught sine squared omega t. The maximum power or the peak power is equal to I naught V naught. Hence, P equal to P naught sine squared omega t. From the graph, the shaded region represents the total electric energy dissipated in one cycle. The area of the shaded region can be found by cutting and making it into a rectangle. From the derivations, the average power is equal to V naught squared over 2R. The relationship between the RMS value and the peak value of I and V can be derived using the definitions of RMS value. From the derivation, it shows that the I RMS equal to I naught over square root of 2 and V RMS equal to V naught over square root of 2. Now, let's try a sample question. Exercise 1. Distinguish between a direct current and alternating current. Okay, student. To answer this question, we need to refer to the DC and AC definition. Now, let's compare our answers. In direct current, the electric charge only flows in one direction. Electric charge in alternating current, on the other hand, changes direction periodically. Now, we will look at another example. Exercise 2. The output of an AC supply is given by the expression V equal to 30 sine 6000 T, where V in volts and T is in second. Calculate the maximum voltage, the RMS voltage, and the frequency of the current supply. Now, try to solve the question. Alright, here's the answer for question number 1. For the maximum voltage, from the expression V equal to 30 sine 6000 T, remember that in our lesson, we have already discussed the general equation for alternating current, which is V equal to V naught sine omega T. Thus, the maximum voltage V naught is equal to 30 volts. Now, The answer for question number 2. Calculate the RMS voltage. From the formula, we know that the Vrms equal to V naught over square root of 2. Thus, the Vrms equal to 21.2 volt. The answer for question number 3. Here is how we calculate the frequency. Remember, frequency is equal to omega over 2 pi. Frequency equal to 6000 over 2 pi. So, the frequency is equal to 954.9 Hz. Now, we will look at another example. Exercise 3. A current of 8 amperes flow in a circuit which consists of a domestic electric kettle and a 240 volt AC supply. Assuming that the electric kettle is purely resistive, calculate A. Its resistance, B. The mean power dissipated, and C. The maximum instantaneous power dissipated. To answer these questions, we must apply the formula of an alternating current through a resistor. For this question, there is no circuit given. Student can try to draw the circuit as shown to answer this question. Note that the voltage and current supply are always assumed to be RMS values. Suppose R is the resistance of the electric kettle. From Ohm's law, V equal to IR. So, the resistance is 30 ohms. The answer for B. Calculate the mean power dissipated. You must remember the formula of mean power of resistor in alternating current. Average power is equal to Vrms times Irms. The answer is 1920 watts. Answer for C. Calculate the maximum instantaneous power dissipated. The peak power is equal to peak voltage times peak current. The answer is 3840 watts. Okay, student. Remember that for calculating the average power, we need to use the RMS value. While for the peak power, we need to use the peak value. We have come to the end of our lesson. Here is the summary of today's lesson. That's all for today. Until we meet again, thank you.